I'm Ramyana Desikin, and I'm pleased and privileged to be a participant in this interview and informal discussion with John Tukey for the ASA project for filming interviews with distinguished statisticians. John Tukey is a former boss of mine, but more importantly, he has been a friend and mentor for over 3 decades. In his depth of insights, his bold and broad perspectives, his manifold contributions both to mainstream statistics and to an amazing range of scientific and technological problems, as well as his involvements in numerous significant societal and global issues, John Tukey is a unique statistical scientist and stalwart in our time. I would like to thank Belcor for sponsoring this videotape for the ASA. A significant component of John Tukey's professional career has been his part in telecommunications research for more than 3 decades in the old Bell system at Bell Telephone Laboratories until his retirement, and his continuing involvements at Belcor since his retirement from Bell Labs in 1985. I'd like next to introduce the other interviewer, David Hogland from Harvard University and Abt Associates Incorporated. David is a former student of John Tukey and a co-author with John of several publications. In a sense, between David and myself, we cover 2 of the major areas of John's professional career, namely his association with Bell Labs in the telephone industry and academia at Princeton. We're also delighted to have John Tukey's wife, Elizabeth, join us today. Many of us in the statistics profession know Elizabeth as the charming and supportive spouse who occasionally sets John straight and always makes everyone feel comfortable and at ease. To start things off, John, one of the characteristics of yours that most of us are struck by is your unconventional thinking, and one hypothesis for this might well be that a cause could be your unconventional education. Another could be that there were many unconventional thinkers such as Charlie Windsor and John von Neumann and Richard Feynman that you've interacted with, and I'd like to get you talking about what the roots of this unconventional and bold thinking might be.
Well, I'm probably the worst person to answer that in some sense, because from my point of view, it's not unconventional. But my parents did feel that it was better that I learned at home rather than going to school for a long time. I ended up doing, I guess, 3 things in the New Bedford High School. The chemistry laboratory, which wasn't very much available at home, mechanical drawing, which wasn't available at home, and a semester of French as sort of a polish. And then I went into Brown based on college boards. And I'm one of the few people, I guess, who used mechanical drawing as a college credit to get in, and went in there with some advanced credit for other things that I'd done. Now, I think rather than that pattern, if you want to talk about unconventional experiences, perhaps it was helping the teachers make a program, do the schedule for the high school and all the students every year. A guaranteed unconventional experience for somebody who's approaching or at high school age is to politely tell the teachers how they ought to do things. And I think I learned certain things without knowing it at that stage. But whether the absence of the heavy routinization that goes with most schooling was responsible or not, I don't know. I think that I think in some general sense this must have been settled by the time I got into or out of college. Specifically as far as statistics go, you mentioned Charlie Windsor. And certainly I learned an awful lot from Charlie, not all of which was statistics, some of which was physiology, some of which was various other things. And as of that time, you could learn things from Charlie that weren't in the literature anywhere. I'm not sure all of them have got in yet, although it's been 50 years.
Well, Ram, I think John started out as an unconventional person, and his mother gave me some wonderful stories, and one of them I'll share with you, and that was that when John was 3, his father was assistant headmaster at a private boys' school in Harrisburg, and John and his father and mother were out riding around on a Sunday afternoon, and his father and mother were starting to discuss whether or not a bridge over the Susquehanna was closed, and they sort of batted it back and forth, and all at once John said from the back seat, "It's closed." And they said, "Well, how do you know?" And first they didn't believe him, and when pressed, he brought out this newspaper that had a legal notice of a bridge closing. And that was what John had read, and it was the first time that they knew he could read. And my mother-in-law said that they realized that they had something unusual, and she felt that either one of two things would happen if he were sent to school in the regular manner, and that was he would either get very lazy or he would be a disciplinary problem. Then you could take it from there.
There may be more that you can tell us about Charlie Windsor, if you will, because he's not, I think, nearly well enough known to most people in statistics as he should be, and I certainly think from what you've said, as you think he should be, and maybe some other people about that time around Princeton that you
well, let me shortcut a version of Charlie. He went overseas with the French service ambulance in the First World War, and when he got to be 18, he came back to join the Army. He graduated from Harvard in engineering, which was possible in those days, went to work for the telephone company, decided that was not for him, went to Johns Hopkins and worked with Raymond Pearl and so on. Eventually decided he ought to get a union card, went back to Harvard, got a PhD in physiology. Their first graduate student who'd never had a course in physiology before he was a graduate student. And I met him at Fire Control Research in Princeton, where Merrill Flood had picked him up from Ames and brought him to town, and he picked me up a few months later.
Ames, Iowa.
And except for a year or so when Charlie was wasting time with a mine research project in Washington, we pretty much worked on the same thing until early '45. And I really learned an awful lot. The simplest fact about Charlie is that the second paper, as far as I know in the world, that he ever used variance components in an analysis of variance situation was Windsor and Clark on the catch of plankton from different kinds of nets. Tippett had used it in one paper in England before that. I spent a lot of time with Charlie, and then later on, after I had been at Bell Labs full-time for a few months, I came back to work with Sam Wilkes' group, and there was Willie Cochran and R.L. Anderson and T.W. Anderson and various other people.
Well, I will say that I think the Windsors adopted John during that period when they were all in Princeton, because he ate dinner with them, I think almost, 5 nights out of 7?
Well, everybody ate out, and Charlie and I usually ate lunch together, and dinner must have been close to that, and on occasion I would walk home with them and spend some more time with Charlie. So it wasn't just in the office.
Up till about the time you got involved in some of the war work and so on, you really hadn't been doing statistics, had you?
No. I went through Brown, and Brown had the perhaps the best, perhaps the second best math library. And I read a lot of things casually, including a fair amount of statistics. So I had a little 3x5 card can box that had various statistical things in it, but I didn't have any practical contact, and I wasn't really involved in the theory. I was a chemist while I was at Brown, and then when I went to Princeton I fell over the fence just before I got there. So I was supposed to be a chemist for a year, but I took prelims in math at the end of the year. And at that point, well, I was a point set topologist with analysis flavor rather than geometry or algebra. And so what I did for a PhD thesis was an extension of convergence techniques to very general spaces, so that you could, that never quite sold as well as it might, and it was eventually replaced by some related things that John Kelly put together. But until the war came along, that was where what I was supposed to be doing, and roughly I think it must have been. There were a few short notes in the analysis area and some things in topology.
But it sounds as if, from what I recall, once you emerged from the war work and so on, most of your work was in statistics at that point.
No,
the practical problems and so on must have played a big role in that.
Well, I got thoroughly converted and was one of the fortunate people who taught a graduate course in statistics before he'd ever taken any course in statistics.
I suspect none of the rest of us can make that claim, and probably very few of our viewers will be able to. Maybe we should move on now, not in any special order, to some of the areas in statistics that you've contributed to on the research side and in other ways. One that extends, as far as I recall, from shortly after the war until the present time is your interest in questions of robustness. Can you give us some perspective on what led you into those in the first place, and where you think they've carried us, and what you think may lie ahead?
Well, as you say, it was the practical problems. There was a question of how should you analyze data on the spread of machine gun fire from specifically a B-29 situation.
This was during the war.
Oh yes, and this was during the last phase of the work at 20 Nassau Street, where we were a coordinating group for B-29 research.
So is that the fire and fire control research, more or less?
Well, the fire, originally it was stereoscopic height and range finders, but that was still fire control. But the point being that the question is, given a pattern from this sort of thing, how is it best to analyze it? Now, if you believe in Gaussian distributions, where you know you ought to be squaring deviations, but also it was reasonably clear that the patterns weren't Gaussian. And the question is, what happened for fairly large samples if you had a mixture of Gaussians? And so I think the first thing I got into was that, where it turned out that 0.2% of a broad Gaussian in with 99.8% of a narrow one, it was now better to use absolute values instead of squares. So it shows that Eddington intuition was maybe better than Fisher's, because Fisher's paper about the mean absolute error and the mean square error, there's a footnote from Eddington which indicates that his instinct was that the mean absolute error might be better after all, no matter what the Gaussian theory produced. and things sort of went from there. Ted Harris, who was a graduate student then, and I looked at things, and there was some evidence that sensible trimming would play fairly well across a reasonable variety of things. Peter Huber seems to quote that 58 paper, which was really never got much beyond an abstract as far as publication was concerned.
Did that then develop into that contaminated sampling from contaminated distributions, John?
Except it was looking more concretely at things in terms of working with trimmed samples rather than working with first powers instead of second powers. And that went on for a while, and then there was the big robustness year in Princeton, the year when Jeff Watson came to take the load off my shoulders, which was a great thought. But he produced enough support from different places, so we really had a big robustness year. I think some people thought that the purpose of this was to codify all the things that had been going on, but it ended up instead by sweeping things forward quite a ways. But we had Peter Huber, and we had Peter Bickle from Berkeley, and Frank Hampel, and so on, David Andrews. It was really a big deal, and moved things on to about as far as we really know now, I think, about practically useful things in the single sample case. Because the by-weight still is about as good as anything if you want to be at all vigorous. We know a lot more about some things. That produced a book with 6 authors. Then later on, we got back into things. There'd been sort of some slight continuity in between. And this eventually produced the book that Stefan Morgenthaler and I edited, with chapters by various people who'd been involved on configural polysampling, where you could do some almost sensible optimization because you could rely on simulation enough. Simulation was essential for the work in the robustness year, and it got more essential later, I think is a fair way to put it. The other thing that became clear is that even if you tried to do things by optimizing in 2 places instead of 1, things would tend to flop up in between, and that probably wasn't the way to get the best thing to use in practice, that the old by-weight, which was smoother, was probably still a desirable thing. But I think the configural polysampling has answered a lot of questions, even though they don't bear directly on what one would suggest to somebody that they do with most sets of data.
Another topic in that general area, John, although I guess it's not necessarily thought of as robustness, but in the sense that it's data-driven and less model-dependent. Another big idea of yours that most people know about and use today is, of course, the jackknife. And that, at least the way I think about it, it has the same kinds of flavor as
well,
robustness.
we've got to remember that Maurice Kanui invented the jackknife.
But not the
but not necessarily the same objectives.
He invented it as a bias reduction.
Bias reduction device.
My contribution was to see that it did a pretty good job of variance estimation. If you have a situation where things are essentially additive in the sense of being linear, then conventional sums of squares of deviations do very well in a wide variety of circumstances. The jackknife says if things are not too curved, you can do a pretty good adjustment for the curvature by going to the jackknife instead of the raw sums of squares. Stefan Morgenthaler and I have been working on the simplest seriously multivariate problem, and maybe we'll get back to this anon, But we've also been looking at the jackknife there, and it's interesting that the jackknife doesn't do much better than T.W. Anderson's asymptotics as far as this particular problem goes.
Moving to a sort of a completely different area as an illustration of your tremendous breadth of things, John, which illustrates, I think, many characteristics, namely your work in time series, which, at least to me, has the angle of telecommunications, engineering aspects, the work with Ralph Blackman that started in time series, the later technological improvements and fast Fourier transforms, and the sort of relationships between that as a statistical tool and many other things that you've been involved in, including the nuclear testband treaty work and the area of acoustics and telecommunications and the applications there, and the geophysics kinds of things that you and Walter Monk have done, for instance. Seems to me that that's a very good example of the same theme of saying, here's a statistical tool, a mainstream statistics thing, but it has impacts on all sorts of other areas, and I wonder if you could tell us whether our perceptions on these are right.
And was stimulated from. The thing that got this one going was when H.T. Buddenbaum, who was Bell Labs' whippany, was going to go to a classified conference on the West Coast and exhibit pictures about how good a tracking radar he had. And he brought some data over to try to get some analysis. And Dick Hamming looked at this and said, but if you smoothed it a quarter or half a quarter, it would be look much better, wouldn't it? So we did and made the slides for Bud, but then Dick and I spent a long time over the next 6 months trying to understand why. And this is what led to the noise color memoranda and the paper at the Woods Hole Conference and all this sort of thing. Geophysics was probably the next important thing, meaning A, probably a little later, various things with the revolving Walter Monk, B, some meteorology when Hans Panofsky came to Johnny von Neumann's computer to reduce some data, then eventually other things involved in seismic things and that sort of thing. And also the aeronautical thing. Because one thing that we got into early in connection was the question of what actually goes on when you fly airplanes in a situation where they will maneuver some, no matter how straight you try to keep them. Because if you're going to think about anti-aircraft fire, this influences where the airplane is likely to be, even if there's no evasive action. And so there was a subcontract to Cornell Aeronautical Laboratory out Rochester way to do this sort of thing, and they instrumented a plane and flew it up and down the lake, which was as near constant conditions as it's easy to find. And then they were going to analyze these things, and essentially this really got one seriously into the cross spectrum, because it is essentially a regression sort of a problem. And the first analysis sort of spat in all our faces, and eventually was traced to the fact that people had been looking at the traces and trying to produce their idea of what was a typical value every so often, instead of reading wherever the trace was at the mark. After they did that, then the analysis straightened out. But I think all the things that I got into in that area
Was there something
had their
particular
roots.
fast Fourier transform, John? That
Well, I'll get to that in just
Okay.
a second.
All right.
Had their roots in one application or another. Telecommunications made good use of this. Mike Knoll produced the first working automatic pitch detector, after which that was proved to exist. Other people produced lots of other different ones that also worked, which is a phenomenon that you need to bear in mind. It makes a difference whether people know you can do it. But I think the driving force, as far as I was concerned, was probably these specific military applications, lots of geophysics. And then I gave a course at Princeton which tried to put things together in a somewhat sensible, structured way. And sort of concealed in the back end of that was something that's probably the roots of the FFT. Gordon Sandy read these notes and produced his version, and Jim Cooley heard via an intermediary of what I'd been thinking about and thought he was just doing a coding job and produced the Cooley version. Of course, as time went on, Dave Brillinger did an awful lot about using related techniques on point processes, which you might not have thought were going to be the natural home of cross-spectral and bispectral sorts of things.
Can I ask a question of you? And that is that it was your work on detecting nuclear underground explosions that got you invited as a technical expert to the test ban talks.
To the technical working group, too, for the test ban talks.
Right.
I was spared the test ban talks, thank you. Well, I had been involved with seismologists.
I know.
And there was a State Department panel on seismology, a more unlikely thing you might not want to contemplate. And I got put on that, and we did what we could. And corollary to that, I guess, why we spent a month in Geneva.
In 1959.
And when I came back from the first meeting, I think I told you then, if not very shortly thereafter, that I thought the atmosphere was entirely familiar. It was very much like the atmosphere of a utilities rate case.
That's right, that's right.
Another area in which you've done a lot over the years and are doing a lot in the last little while is analysis of variance. And I guess I'd find it interesting as one involved in some of the more recent developments to know what got you into that in the first place. And
well, I think that what got me into it in the first place was 20 Nassau Street, fire control research. We had an experimental or observational or both group at Fortress Monroe. This is where Brock McMillan was for a while. And
where is Fortress Monroe?
Virginia.
That's Hampton Road,
Oh, I see. Thank you.
near Newport News. And so we had data to analyze. And the experiments often were factorial in form. And if we hadn't been smart enough, otherwise Charlie would have seen to it that we used analysis of variance when we should. And so I was used to running a variety of things through that mill before 1945. So that I think is what got started. Then just after the war, we arranged a couple of sessions on analysis of variance for IMS. And one, I guess, at a AAAS meeting in Boston following on that was somewhat more applied. But Bess Day was strikingly happy with these meetings because she had gone and worked a year with Sir Ronald before he was Sir Ronald, and came back and found that the Institute didn't think you should take analysis of variance seriously. Well, we managed to change that somewhat. Presumably, analysis of variance and regression represent the two largest parts of techniques of things that are worth taking seriously. That doesn't say that you sometimes don't need something quite that is sophisticated, occasionally perhaps, and that sometimes you need something more, but they're the big pieces. Now, probably late 40s, early 50s, one of Gertrude Koch's summer meetings down in the mountains. Cochrane said that regression was the worst taught branch of statistics. And I said, 25 years later, that I thought that was still true. Perhaps not taught as badly, but still the worst.
Still true.
And I think it's probably still true
It's
now.
still true to some extent.
Yes.
Yeah. So, analysis of variance was in somewhat better shape, but it could usefully do some things. It's an example of where it's easy to believe that convenient leading cases correspond to assumptions. People talk about the assumptions that the thing residuals are Gaussian distributed. If this were an essential assumption, then no analysis of variance would do any good, because I can't remember a case where the residuals were Gaussian distributed. And one thing that came in that line is that I did some generalizations, Jerry Cornfield did some generalizations. We decided to put things together and produce a joint paper, and we produced a joint paper on the pigeonhole model that showed that if what you were interested in was things like average values or mean squares, you required very, very minuscule assumptions to get somewhere. And that's, I think, why things really tend to work. Now,
One theme I know in more recent thinking is trying to account more fully for diverse sources of variability beyond what the data themselves may tell. I don't know whether you feel prepared to comment on that or not, but I'm reaching a little bit for what I know are problems that you don't think are solved in this area yet, and which you and others may work on in the future, and see how you'd like to comment on those.
right. Well, I think what you mean more than anything else is the fact that you had often better think about the sources of variability in a way that includes sources that you either can't estimate or pairs or triples that you can't separate. The conventional approach is you take a model and you're careful not to put anything in the model you can't estimate. And from the practical point of view, that may be a damn lie. And one of the things that was in the pigeonhole situation was that it still worked if you overlapped a collection of sources of variability that behaved individually very differently. So now, I don't think that's something that's going to be soluble in the sense of the classical thing. You aren't going to find a way to specify a model where you can estimate everything. That isn't the nature of the data you usually have. If the model is realistic, there are going to be things in there that you can't estimate, all right? So you have to admit this and deal with them as best you can. I'm sure one of the things you were pointing toward was what's been going on for a while now about exploratory analysis of variance, where you and Fred Marsteller have joined with me in editing at one volume out and at least one more volume coming with separately authored chapters, which really says, let's go to the opposite extreme from the conventional. Let's not ask, do we have to complicate the breakdown? Let's start by making as complete a breakdown as we know how to make, and then ask, to what extent should we put the pieces back together again before we think about them? That seems to be the sensible exploratory attitude. And have we seen any book reviews yet on Volume 1?
I think a couple.
I'm not
One just appeared in JASA recently.
I haven't seen that.
I think the most recent number, and I believe I'd seen one Or maybe it wasn't JASA, maybe it was in one of the other journals. I believe there have been two.
Okay. Did they seem to believe us a little?
I think they're starting to believe us, although maybe they haven't always noticed some of the innovations in the book.
Well,
but,
that can be too. That's all right.
the second volume should move us ahead
Even
more briskly in that direction. I
Yeah,
think,
but even without the second volume, people will catch on slowly.
Yeah.
After all, it's probably true that one of the reasons that Fisher introduced the analysis of variance was to bypass the arguments about the evils of correcting observations for block effects. He just buried this in the algebra, in the arithmetic, and nobody worried anymore for a while. Because I think they really did appreciate that the technique was producing good results. So if not everybody understands everything the first go-around, I'm not going to weep in any beer or apple juice. But I look forward to their catching on slowly.
I think of two other topics closely related, at least in some people's minds, to ANOVA. One of the things that you're well known for in that area is the so-called ODOFNA technology, 1 degree of freedom for non-additivity. I don't think I know originally how that came about either, although that shows up in the 1949 paper and then again more graphically in the EDA book.
Yeah, that was a problem that I carried in my back pocket for about 12 months. Had a feeling that we needed something and didn't see how to do it. And then eventually I did see how to do it. And after this was around, and I don't know if it's published, but it's been talked about, it turned out that the people at North Carolina were actually really quite close. That they were really, I think, essentially using the ranks of the row effects and the ranks of the column effects to multiply rather than the apparent main effects themselves. But they hadn't taken this out from under the table yet. So
Was this Gertrude Cox? And
it was the people at Raleigh. Just who I don't know. I suppose Curly Lucas is as likely to have done it as anyone. The time the word got to me, there were no names attached.
From a little later than that chronologically, many people know of the then, well, up until just about now, famous unpublished book on multiple comparisons. From the historical side, I'm curious, as I am in many of these other areas, about what led you into working on that particular problem. And then I also recall that that's something you've done some more work on, also with a robustness flavor, in the last, say, 10 years anyway, and maybe doing some more, who knows. And could you link the two together for us a bit as well?
Well, the answer is the Baltimore section of ASQC is what got that going, really. I got invited to come down and give a talk on the industrial uses of the range. So I had to A, review things a little, and B, find a few new ones. And so what I regard as the standard multiple comparisons, looking at the range of the main effects against a suitable error term, was produced as one of the things to go in that talk. Dick Link and Dave Wallace were around at that point. Whether Tom Kurtz was right there then or later, I'm not sure. But this eventually led to the range against ranges version, which was, I guess, a few decades late. That there's no reason that couldn't have been done in the 30s or the 40s. Because there was really nothing. It didn't really build on that much, and a combination of simulation and some moment calculations. If it had come along in those days when everything had to be done by hand calculators, then I think it would have been taken over in a fairly large way. By the time it actually came out, the computer, the first inklings of the computer era were along, and doing conventional analysis of variance was no longer a painful task. And so I don't think it ever really got put to use. But it was constructed and expounded with the idea very much that this was something to be used on real data. And the book manuscript was essentially a follow-on to that as things went on. This came along just about the time that Henry Chaffee came out with the version using essentially squared deviations in the numerator, which eventually, I think, even Jerzy Neyman decided that while it was very snazzy from the point of view of theory, it really didn't quite cut the mustard. One, because you get the extra power on the comparisons that you're less interested in, and the contrasts you're less interested in. And secondly, because often it turns out for those you're using the wrong error term. But this has been a matter of continuing interest. Henry Braun and I did a paper which was in the Fred Lloyd Festschrift, and I suspect most people have never seen it, which in a sense shortcut some of the techniques that some of the complicated techniques that some psychologists had been putting together for what to do really when you're deeper into the problem. The studentized range is natural when you're first tackling the problem and your errors are large and the question is, can you find anything? As you work down and you start doing experiments where the standard errors are smaller compared to the differences, you probably want to do something else. For some purposes, perhaps some of Roy Welch's techniques. And way over at the far end, when everything is well separated and what you need are quantitative confidence intervals, you end up back with a studentized range again. But it doesn't hold in between. I don't think we have a full sequence of techniques in between. Henry and I did one, a maximal subrange procedure, which is competitive with the complicated things in the range where you're trying to get nearer to being able to detect the directions of most of the differences. And then of late I've been thinking about generalizations, as you well know, since we have been jointly involved in the studentized phi range.
Yes, indeed.
There's still ground for a fair amount of thinking, I think, in these areas. But I think we're better off than we were.
I've got to say that at one stage in our lives, whenever I would ask John what he was working on, the answer was always multiple comparisons. And that went on for a long time. It's interesting to see that he doesn't think he's finished yet.
Well, that was just the 398 typed pages of the document that's now finally appeared. Lots of other things happened after that, but they happened in a more dilute manner.
Well, just to switch topics altogether now, Elizabeth, and maybe we can call on you to say something about this dimension of John, which I'm sure that most of our viewers would be totally unfamiliar with, that is the area of John's what we might think of as extracurricular activities, general interests, not necessarily tied at all to statistics in any way. And I'd like to hear your story about an example of that. I think is the story of how you and John met.
Yes, well, he was one of the organizers of this folk and square dance group that I guess came into being about the mid 40s. Is that right? Or had it been going since the end of the 30s?
Well, I got embroiled partway through the war, and it had been in existence for a while, and I have no idea when it really started.
Well, the reason I don't know is that I didn't come to Princeton until 1946, but it was well known and well patronized. On every Tuesday night there was this folk and square dancing group that met in the old elementary school at 8 p.m. And mind you, when I came along, it was just after the war, and there were many more men at this group than there were women. And John was one of the teachers. There were about 3 or 4 different people who taught. And I had been to this dance several times with my sister, but she had been at college during the war and was used to the fact that you went to dances without any partner, whereas I was not. And if some young man didn't ask me to a dance, I certainly didn't go. But she got me out by getting after me. And I said, well, I will go and be your chaperone. And I sat on the sidelines with my coat on, and anybody who asked me to dance, I declined. And I did this for 2 or 3 different weeks. And there was one night when there was such a shortage of women that I really felt embarrassed not to get up and participate in a Paul Jones. And I think I did participate in 2 Paul Joneses that night. So about a week later or 2 weeks later, when I went again, my sister and I were early, and John was there, and he had he was the only one that was there among the teachers, and he had all of the records. And so at 8 o'clock he put a record on and walked across the room in my direction, and I thought, well, I don't know him, so he's not coming over to say anything to me. But I looked over this side and I looked over this side, and there was nobody on either side of me. So I realized he was coming to ask me to dance, and I accepted him. He asked me to dance every single dance that night, and I ached for 2 weeks afterward. So that was how I met him. And I will say one final thing, and that is that when I finally gave up square dancing was sometime, probably getting along toward 1970, where in a square dance, as we were swinging around, I got a cracked rib. So at that point, our square dancing days diminished, but it's always fun to do, and I notice that there are people in their 80s who do it. We maybe ought to start again, John. The other thing that he's gotten interested in lately is birding, and that is something that he's been gradually doing more of all the time, and he loves it. And Lincoln Moses, I think, was the one who really started him on this, because they used to, when we were in California all during the 60s, each summer, John and Lincoln would go out in Lincoln's old convertible and drive all around the back roads of California that were within a day or two's range that they could get out and get back. And I think in the process that John got exposed to birding. And the other thing that he's been very good at, and this I think goes back to his childhood, is gardening. He worked with his father a lot, and they were companionable equals. And John's father was very much like John, and they would talk while they were gardening. And as a result, John considers gardening is a social thing. And as many people know, he's invited them to come out and garden with him. And sometimes it's been thought that I was the one who put him up to this, but I never was.
John, there's another characteristic of yours that most people are very well aware of, and that's your fun with creating your own terminology and vocabulary. I'm not so sure that many of the viewers would be aware of the fact that amongst your many inventions of words and terminology is one that is commonplace today, which is bit for binary digit. And with that and words like ANOVA, we've talked about analysis of variance, to things in time series of Kepstrom and frequency analysis and a variety of things. I wonder whether one gets the impression that you have at least half the fun in the things that you do is really creating this terminology to describe what is something that is very meaningful to you. And I wonder whether you'd like to comment on that. And Elizabeth,
may I
you can
comment on
sure.
that? I took a course in statistics at Stanford one summer, and because I'd never had any calculus, I took it in the psychology department. Having been an English lit major in college, we were taught never to parrot anything that you read. Well, I almost failed that statistics course because I took the definitions in statistics and tried to put them in my own words. And the thing that I realized about John is that he didn't have that kind of a rigorous education in English composition, English literature, so that he felt free to put the words together much as you would math symbols. And I find that very interesting.
Yeah. No, I would do it a little differently, I think, than either of the two of you. The worst source of confusion is the use of one word with too many meanings. And the most obvious thing for many mathematicians and most statisticians is the word independent. Goodness knows what independent is going to mean the next time you meet it. So this basic view has always driven me to say, if we want to talk about something that's rather like something where we have a word, it may be important that we have a separate word to describe it. I think the most obvious example is hinges, or as some circles prefer, fourths, alongside of quartiles. There were two or three specific definitions of what a quartile was, and for the sorts of things in EDA one didn't want to use any of them, for specific and I think good reasons. So it was desirable to have a word. According to those who remember, and this is written down in the annals of the history of computing somewhere, bit was a luncheon table remark. And all I have to say is that if it prevented the alternatives of Binet and Bidget, then I am very happy that it took hold. I think in that case, it's perfectly clear that a word was needed.
Yeah.
Right.
And in this case, I think a shorter and snappier word with the other alternative interpretation still correct was what should have come to pass and what did come to pass.
I think we could go back into some applications. A lot of things that you've done aren't necessarily as visible in the technical literature of statistics because they haven't resulted in usual sort of journal publications, although some of these topics have received a lot of dedicated time over a period of many years, and I think we want to hit several of those. Let me start by asking you to comment on things generally in the biological and biomedical sciences and the environment. I know you've done some work on various pollution issues and also some work related to clinical trials, and have recently been involved in some projects that have brought you to Cambridge from time to time under the auspices of the Health Effects Institute. I don't know whether this all provides a reasonable rubric or not.
Well, it doesn't matter.
Tell us
It
about
provides-
some
it
of those
provides
things a little more.
Provides a set of stimuli, and I should try to respond to at least some of them. I was once asked to give a talk, I forget whether it was AMS or MAA, on what mathematics can do, I think, for the federal government or something of that sort. And I said I wouldn't do that. I'd be willing to talk on what mathematicians could do for the federal government. A lot of the activity in the areas, some of the areas you were pointing to here, is not statistical at all. I spent a term on the President's Science Advisory Committee. Essentially nothing I did over that period was statistics, maybe a little occasionally. I was on the research committee at Health Effects Institute for a dozen years. About 3 or 4% might be statistics. I had the advantage of at least an education through the master's degree in a concrete science. And a lot of these things, the contributions that I've made, I think, have been as a philosopher of science, as somebody who understood about scientific technique and so on, reasonably generally, and not necessarily tied to statistics at all.